right, so let's do one last one of these. We're going to look at a circular hoop of mass m, this guy here, and radius r, and it's going to oscillate. So basically we're going to look at something like this. It's going to oscillate under gravity. At any particular time it'll have some angle theta. And it's just a hoop going around like that. And that's pretty much all it is. So this is something that you saw previously. You probably saw it on the Walter Lewin video. It may have shown up on two of them. And it's just something that you need to see. So I'm going to show how to do that. Not in the way Walter Lewin did it, but in the way that I'd prefer you to do it. And this is sort of important. So if you look at the tutorial, it's going to go into some detail for some of the places where the procedure that Walter Lewin used does not work. Now, you could make it work, but you'd have to do a lot of extra work to make it work with that, silly formula that he uses. So, now we're just going to start with that. Right, we had some sort of bar here with a hoop on it and some angle theta. That's more or less all we need. This has a mass m and a radius r. And that's what we want to put over here. So we have our hoop. I think it's a hoop. It is a hoop of a mass m and a radius r. And we need to find the oscillation frequency. And we'll give that an omega. I think Walter Lewin used the period. They're basically the same thing. This just saves you a step. Or saves me a step, actually. All right, so how do we sort of analyze this? So we've pulled the stuff we know out. Now we want to analyze the problem. Well, we want to do something with this. Now, in fact, we draw our extended body diagram. What we want to do is we want to put the axes at the pivot point, which is right here. And since there's only one force here, if we have collinear forces, the best way to draw this is to pretend that the hoop is a bar. It has some weight coming down here at the center, which is where the weight is applied. It's at the center of mass, which is in the center of the hoop here. It's not anywhere where there's actually any hoop. So the weight's coming down from there. We have to label our axes y and z. And there's a normal force coming up here that's not going to be important because it's at this crossing point, at the axis crossing point, at the pivot. And what I forgot to do was say that there's absolutely no net force and no net... Oh, wait, that's not true. There is a net torque here. I theta double dot, and there's no net force. All right, so we need a concept, and this will be rotational dynamics. This is the rotational analog of Newton's second law, right? So the equation for that is the sum of the torques is equal to I alpha, or I, in this case, theta double dot. We're going to have to use that because we're doing the simple harmonic motion. Or this is the complex harmonic motion. That's okay. It's still simple harmonic motion. It's a physical pendulum, not a simple pendulum, but it's still simple harmonic motion because we're going to make a small angle approximation somewhere. So that's sort of the deal we're going to use to make this guy work. So we want to find that frequency. We're our plan, we're doing our physics. How do we do that? Well, we do it with our analogies, right? So we have our simple harmonic oscillator analogy. That's how we figure out what the frequency is if we can get our equation, or if we can get our math to look something like this. The theta double dot plus some constant, which is going to be the square of the frequency, so that's this guy, times theta is equal to 0, then you have simple harmonic oscillations, and we can just take whatever is multiplied by theta later on, and that will be our frequency. Now we don't need to find theta because this is fairly simple. I think somewhere I gave you a fairly complicated one earlier that did require finding x or something like that, or finding x as well as x double dot. But for this one it's fairly simple, so we don't have to do that. Then we need our rotational dynamics, R2. That's going to let us find the theta double dot. See, it's right there. So we add up all the torques. Should be careful with torques, so we'll use an entire line on the torque because you have to be careful with what's going on there. And that's equal to I times the angular acceleration that we're looking for. We don't know the moment of inertia, and we don't know the torque, so we have to figure out what those are. Okay, so remember the torque is equal to the position cross the force. So this is the place where the force is applied right here from this spot coming down here. The normal force here doesn't produce any torque because it's right here at the pivot point. So it's at the fixed point. That point does not move, and it doesn't, and you can't actually create any acceleration there. Here is where we go, and this vector is r from the pivot point to the point of application, right, from here to here. And then the force here is just going to be the weight, right, which is going down. So they're non-collinear, which means there is a torque, and they're not parallel, so there's a torque, and they're not perpendicular, so it's not just taking the magnitudes and multiplying them. I guess in here we have to have, I forgot, our direction, x hat. All right, so what else do we need? Now we have the torque and the, oops, this guy was a question mark. The torque and the moment of inertia, so let's go with the torque first. Right, so we're looking at that guy there. We have to figure out what r is. Right, so this thing has a radius r, so r has a magnitude of r, big R, that radius, because the center of mass is right in the middle of that ring. And then we have to multiply it by the unit vector this direction down here. So remember, this is our angle theta, so it's coming down from the top there, so the opposite direction is the horizontal direction. So that's sine theta, so it's in the y direction. That's 1/2 of our unit vector, and the other half is the cosine theta in the vertical direction, or z. So again, this is, we could have found this with, this is the definition of the vector, right? Magnitude times direction. So we put this in here, and we have our sine theta y hat plus, or minus, excuse me. Ooh, it's going down. Gotta remember that. It's important. Minus cosine theta z hat. And then we have the weight, which is mg minus z hat, as usual. All right, so I know our theta we said we don't care about. We're looking for tau m. I know g I'm allowed to know. And everything else is a direction. All right, 4. What's left? Well, we've got that torque, so we only have the moment of inertia left. And we're going to find that with, well, is this at this, this is not oscillating at the center here, right? Is this oscillating at the center of the ring? No, it's oscillating at the edge of the ring, so we have to use the parallel axis theorem. So that's I is equal to the center of mass. moment of inertia of a ring, which is mr squared. You have to look that up. Plus the displacement term. So the displacement term is the additional inertia, moment of inertia, rotational inertia, from moving from the center to the edge, which is always the mass of the object times the square of the distance between the two axes. This axis here and this axis here. So they're coming in and out of the screen. So that's eventually just going to be 2mr squared. But there's no good reason to put them together until you put them together. Part of the reason for listing these out is so that you're clear about what you're doing. It makes it easier if you make a mistake. If you said that was 1/2 mr squared there and you notice it later, it's easier to scratch that out. And it's actually easier to notice that that's where you made the mistake. All right, so now that we're done with the physics, it's time to do the math. Always start with the hardest part. If there's a hard part, usually there isn't. The hardest part is the cross product, right, which is it's actually a fairly easy cross product, right, because we only have z hat there. So remember, y hat cross z hat is equal to x hat. So that's one thing, and z hat cross z hat is equal to 0. So since we have the cross product here and we have the z hat, that cosine theta is not important, even though I pretended it was important a second ago. That disappears because z hat cross z hat is equal to 0. So all we have is y hat cross minus z hat, which is going to be minus x hat. So we'll have the torque is equal to mgr times minus x hat. Okay, and that's got the right units. That's the right way to go. All right, so now that we have that, we can take this, plug it in there, and this, put it in there, and then we can have an equation that will be sort of useful. So let's substitute a and 4 into 2. All right, so that means a is oops, I forgot the sine theta. Sine theta is important. Mgr sine theta is equal to, and there's a minus sign there, 2mr squared theta double dot times the angular acceleration. It's supposed to be a square. Okay, so now that we have all that, what do we do? Well, we'll take b and we'll simplify b a little bit. Right, these m's cancel, for example. I can get rid of that r and that r. And we can also use the approximation. Sine theta is approximately equal to theta in small oscillations. And I can move this guy over here and switch everything around. So we have 2r theta double dot plus g theta, right, because that's an approximation, is equal to 0. So that's almost in this standard form here. We have to divide through by 2r to get into standard form. So put c in standard form. 1, so that is theta double dot plus g over 2r. Theta is equal to 0. Good. And so E is analogy, D with 1. It's going to give us omega squared is equal to g over 2r. And basically, that's the answer. That's what we need to figure out. Okay, so this question here is, what about my symbols? I've got G, which is a universal, and then I've got R, which is here, and then I've got a 2 that I don't care about. So we're good. We've got the things, everything in there is something we either know, the radius, or something that we can assume. And we didn't have to know the mass, but we did anyway. I don't know what that little dot is. Okay, let's see. Dimensions. Well, dimensions of omega squared, which is what I've got there, is t to the minus 2. And here we have dimensions of g over r are equal to dimensions of g times the dimensions of, or divided by the dimensions of r. So that's L t to the minus 2 L minus 1, which is t to the minus 2. Okay, so they check out. Checkity check, check. Everything's good. That's the basic idea behind how to look at these simple harmonic oscillator things. Now, I know you saw this a couple of times from Walter Lewin, but usually people just focus on, the answer, and that's not the way to really do things. The thing to do is to really focus on the process, because this process will let you find this omega squared for more complicated situations than, I think it's omega squared equals, what would it be? mg over I. I think that's how they do it. So it's a little better than that one. It keeps you a little happier. It works better. It does what it's supposed to do. So this guy has a lot of restrictions on it, and you'll see that in the group homework and in the tutorial, and in some of the regular homeworks too. This equation doesn't work, and that's why I gave you those problems, because I want you to work it out like a college student, right? So this doesn't always work. Occasionally it does, but not always. This process always works. Well, I mean, as long as you do it right, it works. But that's true of anything. So that's a way to do it. Now, I should mention that not everything will be amenable to using this technique. So this is the torque technique. There's a second technique, which is using the energy. Now, we used the energy with simple harmonic motion some time ago, and you've seen Walter Lewin do it as well. And I think you've seen it for some of these things. So what would happen is, if you have a situation where something's rolling, then you might, you have a homework problem where you've got some device like this, where you've got a spring attached to a wall over here. Well, this guy's rolling, and that's not really going to have anything to do with the torque. That torque, whatever's causing this to roll, there will be torques on it, but have nothing to do with this spring constant. So the way to look at that is through the energy, right? And then take the derivative of the energy. Remember, the energy is equal to k plus u, and dE dt is equal to 0, which means that if you properly formulate the kinetic energy of this thing and add it to a proper formulation of the potential energy of this thing, then you can use the derivative to get it into standard form. Sometimes, depending on the actual circumstances, you might have to use the approximations, right? So you've got what, the sine theta is approximately equal to theta. That's good for the torque method. When you're doing this with energy, the potential energy is going to be equal to something like mg1 minus cosine theta. So instead, what you're going to have to use is the cosine expansion, which is 1 minus 1/2 theta squared plus a bunch of stuff. It's actually plus and minus and plus and minus and plus and minus and plus and minus, but you've probably seen that much calculus by now. All right, so I don't know if you have it, but I assume you have. So that's about it. So those are sort of some tips for that. And this is the last one of these. And I hope you have a really great summer and are looking forward to the final and all those other good things that are coming up. So we've got a quiz coming up, and then we've got a final coming up, and then you've got a summer coming up, and you should think about what you're going to do with all that stuff. I think I have some reading material that I generally put up only at the end of the semester. That's up online that I think is good. There's some things that might help you out. Some explanation of what's really going on with electromagnetism. It's by Richard Feynman, and there's some other things about studying and math and stuff like that. Things that if you like them, if you want to do a little bit extra work over the summer to prepare yourself for the next semester, they're available. You can pick them up online. I'm not sure how many of them are in ebooks and how many of them aren't, but because I never read ebooks, so I don't know what is happening here. But anyways, have a great time, and I will talk to you later. Bye now.